All right, guys, welcome to lesson 7.4. We're going to begin talking about area and volume. Lesson 7.4 is where we talk about how to find the area that exists between two curves. So that's our goal for the day. So let's go ahead and introduce the concept here a little bit. Suppose I have a function f of x that looks like this, and suppose I have another function g of x that looks like this. Now, if I want to find the area underneath of the function f of x, as you guys know, the way that we would go about doing that is by setting up an integral. Let me lower this a little bit. You would set up an integral of the function f of x. Now we need to start at the beginning point of the function and end at the ending point. And so we'll call those points A and B. And if we go ahead and integrate that, that would give me the area under the curve of f of x, right? So this shaded blue region would be the area represented by this integral here. Now, if I wanted to find the area under the curve of g of x, I would do the same thing. It's just that instead of doing f of x, I would integrate the g function. So let's do that. Represented by that red area there, we're going from a to b, and that would be g of x. So now I have two different integrals here. One represents the integral of the function f of x, which is the area under f. The other integral is of g, and that represents the area under the g function there, which is represented in red there. Now, if you want to find the area that exists between those two curves, so just this region here, what I would have to do is I'd have to keep the blue area but take the red area out of it, like that. And now I'm left with the area that exists between the curves. Well, if I'm taking away the area of g, that means I'm subtracting this integral of g. So if you want to find the area between two curves, basically you just need to find the area of the top function, the one above it, and subtract from it the area of the function that's underneath of it. And what you're left with is the area between them. Now, we do have a property of integrals that says if you're integrating two functions that have the same limits, then basically you could rewrite this as an integral of the difference of the two functions themselves. Okay, so this one here would represent the area between the two curves. You could do it separately like this, but we're going to be doing it mostly like this. So basically, if you want to find the area between two curves, you do the area of the top function minus the area of the bottom function. In other words, you do the integral of the difference of those two functions. Okay, so that leads us to our slide here that kind of explains the whole process. So how do you find the area between two curves? Well, if f of x is greater than g of x, and what that means is that f of x is the top function and g of x is the bottom function. If f of x is greater, that means its y values are higher, and if the y values are higher, that means they're greater. In other words, you have the top and the bottom here. So if f of x is greater than g of x for all the values of x on the interval from a to b, then the area between the curves is given by top minus bottom on that interval. Okay, now that means they would look like this, and you could technically do the integral of them separately, but that will find for you the area between those two curves, represented here by green, where a and b are the limits of the integration. So let's go ahead and jump into an example here to see if we could do it. I want to find the area between these two curves represented by this region R here. Now, as you can see, the area between them starts here where they cross at the bottom and ends here where they cross here. Now, this is a nice situation. We don't have to find where these functions are crossing. We could see that they cross at x equals 0 and they cross at x equals 3. So I'm going to be integrating from x equals 0 to x equals 3. And we want to do the top function minus the bottom function. So as you guys can see, the top function, the one that's on top, is the blue line, and the red line is underneath of it. Now in the directions here, they tell us the equations of those graphs. They tell us that we have y equals 3x, that's one of the lines, and we have y equals x squared. Now you might be wondering, well, how can I tell which function is which? Sometimes it's easy to tell, and sometimes it's not. We'll talk about how to deal with that later. But for now, I think that we should all understand now that y equals x squared is a parabola, and so that would be the red line. So this one is the bottom function. I'll put b there for bottom. And then this one here is a straight line. This is a linear function, so that would be the one that's on top. So if I want to find the area between the curves, we integrate from 0 to 3 with the top function minus the bottom function. Okay, now you could use your calculator to get this, but sometimes you're not allowed to use your calculator. And this is a pretty simple integral to calculate, so I'd say let's go ahead and just do the integral. All right, so the first thing we would do is we would integrate the function, and I did that simply by using the power rule. Okay, the next thing we would do is we apply the fundamental theorem of calculus. That's where we plug the 3 in, and we also plug the 0 in and subtract them. Now anytime you're doing the fundamental theorem of calculus by hand, you're going to want to set up like this. This will help you make sure that you're not being messy with your work and you're being organized, which will prevent a lot of the basic math errors that come along with this type of problem. The first parenthesis set is what you get when you plug the 3 in. The second parenthesis set here is what you get by plugging the 0 in. And before I even plug those numbers in, I like to replace the x's with parentheses, and then we're good to go ahead and start plugging those in. So for the first set, we're going to plug in the 3. And then for the second set, we're going to plug in the 0 for the second set. Okay? All right, and then we're going to go ahead and calculate these. And before I do, I want you guys to notice that since I'm plugging 0 in here, this whole piece is just going to go away, so I can ignore that. So if we go ahead and simplify this, I'm going to end up with 27 over 2 minus 3 over 3. Now we do want to get a common denominator here. How you do that is up to you. I personally notice that this is 3 over 3 is the same thing as 1 over 1, so I'm just going to reduce that. And then all I need to do is multiply the top and the bottom by 2, which will give me 27 over 2 minus 2 over 2, which is 25 over 2. And then we're all done. So this 25 over 2, in other words, about 12.5, if you want to write it as a decimal, is the area between those two curves. All right. Now what I want to explain before I move on to example 1b is that on our integral, we went from 0 to 3, and that's because the area started here and here. In other words, it's the place where the lines intersected. And a lot of times these limits of integration will come about where those functions are actually intersecting. But it's not always like that, so let's take a look at example 1b. On example 1b, we have two functions here. You guys can see we have this parabola and a straight line again. But you're noticing that the parabola and the straight line don't actually cross, but there's still an area between them. Now when that happens, since the functions don't cross, the problem will actually have to tell you where to start and where to stop. So let's see if we can identify the functions here. First of all, I have y equals x squared plus 3. Well, that's a quadratic, which means that's the parabola here. Okay, so that's clear. You're noticing that the skill involved in this process is you need to be able to know which line is which. So that's a quadratic, so it's a parabola. This here looks like a linear function, so that must be this straight line here. Okay, now you'll notice in the directions, though, that they're giving us two other equations, x equals 0 and x equals 2. But why are those there? They're not actually lines that are on the graph, but what those are is those are your boundaries. X equals 0 is a vertical line, okay, at x equals 0. So here's the vertical line at x equals 0, and then x equals 2 is also a vertical line. Anytime you have x equals a number, that's a vertical line. And so x equals 2 is right here. You guys see where that's at x equals 2? And so the purpose of the x equals 0 and x equals 2 is that those are our limits of integration. So the functions don't have to intersect, but if they don't intersect, then the problem that they give you will have to clarify what the starting point is and what the ending point is for the area that we're interested in. Okay, so let's go ahead and set up this integral. So we're going from x equals 0 to x equals 2. That's those numbers there, right? And we want to do top minus bottom. Now in this case, the top function is the parabola. The parabola is higher than the blue line. So that one's going to come first, x squared plus 3. And we're going to subtract from that the line underneath, which is y equals x, and so that goes here. And so there's our integral. All right. Now we're ready to go ahead and do the integration like we normally would. So let's go ahead and integrate our function. And once again, by applying the power rule of this function, we would get this. And then we're going to go ahead and set up our fundamental theorem of calculus. So I've plugged in the 2 and the 0 there. And then we're just going to go ahead and calculate it. Now this doesn't always happen, but it's happened again here, and I'm doing that on purpose just to kind of keep the problems quick and simple. But when you have a 0 here, everything just goes away, right? So we don't have any numbers over here to work with. But you do want to remember, if you ever do have numbers over here, you have to distribute the negative to all of them. But what I'm left with over here is just 8/3 plus 6 minus 2, which leaves me with 8/3 plus 4. And you could think of that as 4/1 and get a common denominator by multiplying the top and the bottom by 3, which gives me 8 plus 12/3, which is 20/3. And that would be the area between those two curves. All right. So I think we're pretty well equipped now to let you guys go ahead and try a student practice here. Now you have some unfriendly numbers to work with here, but just go ahead and do your best. Pause the video here, give it a try, and when you unpause it, I'll have the solution up for you. An important thing to pay attention to is the fact that it says it's in the first quadrant. So we're only interested in this first quadrant over here. I don't care about anything over here to the left of the y-axis. And so this is the area that we are interested in finding. So if that's the area I'm interested in, we could see that we are going from x equals 0, which is this line here, and this dot over here. So we're going from the left to the right, so from 0 to 1.5. Then we do the top function minus the bottom function. The top function is the linear function. The bottom function is that curving line, which must be the e to the x. So top minus bottom would look like that. Then we go ahead and integrate it, which would look like that. Then we go ahead and apply the fundamental theorem of calculus, which would look like this. Now we got to be careful here. These are both 0, but e to the 0 is not 0. E to the 0 is 1. So we have minus a -1 there. Why is it negative? Because there's a minus in front of it. On the left side we have, and we would get this so far, 6 times 1.5 is 9. This whole fraction here becomes 1.125. The double negatives here can become a positive. And what we could do is we could just combine these regular numbers together. I haven't done anything with the e to the 1.5 yet. But by combining the 9, then 1.125, and the 1, we get 8.875. Now if I subtract from that e to the 1.5 using my calculator, I would get about 4.393 if you wanted to round it to the nearest thousandths, which is what we usually do. Okay, and so there you guys have it. That's how you can find the area between two curves. So let's take a look at another twist on the problem here, a little bit more we can do. I've titled this Finding the Intersection Points. Now sometimes if you want to, they won't tell you where the functions intersect, even though they want you to use that point. So you have to find the intersection point yourself sometimes. So here it says, let S be the region in the first quadrant. And by the way, that's a really common thing for them to say, is the first quadrant, which means we're only looking at this much of the graph here. I don't care about anything to the left of the y-axis or below the x-axis. So let S be the region in the first quadrant bounded by the graphs of the cube root of x. Now, that's a weird function, so I'm going to assume that's probably this curving blue line here. And the horizontal line y equals 2. That's the red line here. Y equals 2 is a horizontal line, in case you guys forgot. So the horizontal line is the one that's on top, and the cube root of x is the one on the bottom. And we're only looking at the area in the first quadrant, as shown in the picture. So that would be this area here. So if I want to do my integral, it's obvious that we're starting here at x equals 0. And just so you guys know, anytime they say that you're in the first quadrant, that's a lot of the times, not always, but that typically will be the starting point is 0. It's possible that they may intersect after 0, and so you start somewhere else after 0. But in the first quadrant, a lot of times the starting point is 0. But I don't know what my other point is. I don't know where I stop. I go from x equals 0 to something, and I need to find out where they cross. Now, we've done that before in this class. How do you find where two functions cross? And the answer to that question is you set the two functions equal to each other and solve for x. And so now in my instructions here, I put and or y. Sometimes you do want to find the y value. We'll get to that in later lessons, but for now, we really only care about finding the x. So let's set the functions equal to each other. The cube root of x needs to be set equal to the other function, which is y equals 2. Okay, so how do we solve this? Well, the way that you cancel out a root is by raising it to a power that matches the root. And so the cube root of 3 to the third power cancels those out. I'm left with x, and so x equals 8. And so it's crossing here at x equals 8. So I'm going to be integrating this from 0 to 8, and we want to do the top function, which is the red line, and that's y equals 2, minus the bottom function, which is y equals the cube root of x. So we're just going to put cube root of x there. And we integrate with respect to x. Now, before we begin, you might want to recall that if you ever want to integrate a radical function, you need to change it to a power of 1/3 in this case, because it's a cube root. Now we'll go ahead and apply our power rule to this and integrate the function. And this is what we would get as results of doing that. The next thing we're going to do is we're going to set up the fundamental theorem of calculus, which would look like this. Now I want you guys to notice that over here I just put 0 because once again we're plugging 0 in here, and in this case the 0 does make everything just become 0, so there's no point in having the second bracket or parenthesis set. And in case you guys are wondering, from now on you can just skip that if the bottom number is 0 and you know that it makes everything a 0, but you got to be careful. It has to actually make everything a 0. It can't be like the problem where it had the e, because that doesn't make a 0 in that case, right? All right, now we're going to go and simplify. So 2 times 8 is 16. And now we're going to have trouble here probably. So let's talk about how to simplify that. First of all, we have 8 to the 4/3. And that can be rewritten as the cube root of 8 to the 4th power. The bottom number of the fraction represents the root. The top number represents the power. The cube root of 8 is 2, and 2 to the 4th power is 16. And so what I have here is I've got 3 times 16 over 4. Okay, now I could do 3 times 16, which is 48, and then divide by 4, or you could divide the 4 into the 16 first to make it smaller. Either way, though, you get 12, and 16 minus 12 is 4. So my final answer there is 4, and that would be the area between these two functions. But aside from all the other small details that we talked about, what is important here is how do you find where two functions intersect if they don't tell you? You set them equal to each other and solve. Okay, so let's go ahead and see if we can throw one of these at you guys here. Go ahead and try this one. Pause the video here and solve the problem, and when you unpause it, we'll have the solution being worked out for you. So here's the first step, which is finding where the functions intersect. You set your two functions equal to each other and solve. The first thing I did was I subtracted the x on both sides, which gives me this. I rearranged these because I like to have my subtraction in the middle when I have a difference of squares. And to factor a difference of squares, you just take the square root of each one. You make one a plus and one a minus. So you have 2 minus x and 2 plus x. You set each one of those equal to 0 and solve for x in each case, and you get 2 and negative 2. So that means that we're starting here at this point, we're ending here at this point, and it starts at negative 2 and it ends at positive 2. And so we're looking for this area. So we'd be integrating from the negative 2 up to the positive 2. It looks like in this region that the parabola is the one on top. So the negative x squared plus x or plus 4 goes on top, minus the linear function, which is the red line, y equals x goes on the bottom. So we have the top function here minus the bottom function there. And then we're going to go ahead and just simplify and solve this. Before we begin this one, you want to combine the x's. The positive x and the negative x cancel. So we basically end up with negative x squared plus 4. Then, applying the fundamental theorem of calculus, you're going to get negative x cubed over 3 plus 4x. And then from there, we can go ahead and calculate. And we end up getting 32 over 3. So I'll let you guys study this. Just some things to kind of keep in mind if you're checking your work and you didn't get the right answer here. When you cube a negative, it stays negative. And since this negative had a negative in front of it, you end up with a positive 8/3 here. Another thing to pay attention to is this negative on the outside is going to distribute to both of these numbers here, and it's going to change their sign. So it becomes negative 8/3 and positive 8. The rest of it, though, I think is pretty self-explanatory. All right, so let's take a look at some other things to keep in mind. So if they don't give you a picture, if you're allowed to use a graphing calculator, just make your own. That's pretty simple, okay? But a lot of times they won't give you a picture, and it's a non-graphing calculator type of question. And so what do we do if we can't use our graphing calculator either? Well, the first thing you want to do is find where they intersect, and we've already talked about how to do that. You set them equal to each other and solve. The next thing you want to be aware of is which function's on top and which one's on bottom, and you can't tell just by looking at the picture anymore. So what do? It's a little bit less obvious. Well, you have two options. One option is faster, but it's more prone to error. The other option takes some time, but it's less prone to error. So let's talk about the two options. The first option is the longer one. What you can do is let's say I have two functions f and g, and I want to find the area between them. Well, I know I need to integrate those functions from a to b, right? And I'm going to subtract them, but I don't know which one should really come first. Should it be f minus g, or should it be g minus f? Well, what you're going to do is you're going to pick a number between a and b, some x value between your limits, and you're going to plug it into each function. The one that comes out greater is the top function. Why is that? Because when you plug an x value into your function, it's a y value. So if you plug an x value in there, you're getting a y value. And if the y value is greater on one function than another, that means it must be the higher function. And so basically just pick a number between your limits, plug it into each function, and the one that comes out greater is the top function. So that takes a little bit more time, but it's more precise. The other option is just to take a guess. Now, why is that okay? This is especially useful for multiple choice questions. And the reason that that's okay to do is because the integral of f minus g and the integral of g minus f will give you almost the same exact answer. The only difference is that one will be positive and one will be negative. And since we're talking about area, we're not going to be using the negative one. So let's just say that you just take a guess and you put the f first. Well, you're going to get the same answer, but if it comes out negative, that just means you put the wrong function first. Now, in a multiple choice problem, that's not really a problem. You just pick the same answer that they're giving you, just opposite sign, right? But on FRQ, that really does matter. You would have to go back and reverse everything because they grade your work on those. So I would say option 2 is cool if you're on a multiple choice test. I wouldn't go with that, though, on an FRQ test. I would say option 1 is. I'm going to be teaching mostly option 1 here, but just giving you some heads up about option 2. Now, a third thing you can do, it's not as helpful, but you definitely need to find out where they intersect. You definitely should take some time to ponder at least which one's on top and bottom. But it's also kind of helpful to maybe try and sketch the picture on your own. Maybe you know what the functions look like. We already know that if you want to graph a line y equals a number or x equals a number, we know what those look like. Those are vertical and horizontal lines. Y equals a number is a horizontal line. You might want to write that down if you didn't know that. And we know that x equals a number is a vertical line. So you might want to write that down also if you didn't know that. So those, a lot of times they give you these types of lines in those problems, and so those are really easy to sketch, and then you just have to fudge the other one that maybe you don't know what it looks like. So you do have some options when they don't give you a picture. So just to review, use a calculator and graph it if you can. But if you can't, find where they intersect, find out which one's on top and bottom by plugging a number in, and then maybe even sketch the picture on your own to see if it makes sense. Okay, so we're going to take a look at a problem like that now. And I'm going to add here no calculator as well. Okay, so let's begin. Write but do not evaluate an expression to represent the area bounded by the graph of y equals x over 2, y equals 1, and x equals 2 in the first quadrant. Now, before I jump into solving the problem, I want to talk about this phrase up here, write but do not evaluate the integral expression. This is a pretty common thing that they'll write on the test. And what that basically means is you don't have to actually calculate the area. They just want you to set up the integral. So once we get this far, we're done. Okay, you just have to get the integral correctly set up, and then you can stop. All right, but in this case, we're going to go ahead and just use these numbers here. So let's begin. So first of all, we have to recognize what these things are. I have this function here, and I have this function here. Those are my two functions. One of those are my top function, and one of them is the bottom one. How do I know those are my functions? Well, because those are the those are the y equals equations. We talked earlier in the lesson about how these vertical lines here, those are typically going to be your limits. So that's one of my limits. Okay. And once again, they are telling us that we're in the first quadrant. A lot of times that means that your limit is x equals 0, but not always. If these things intersect somewhere in that first quadrant, then that will be our limit. If they don't intersect, then we'll just start at 0. Okay, so let's begin here. So step one, let's find where they intersect first. We want to see if they intersect in the first quadrant. Do they intersect in the first quadrant? If they do, then that will be my starting limit. If they don't intersect in the first quadrant, then that means my starting limit is just going to be 0 because we're in the first quadrant. All right, so how do we find out where these functions intersect? Well, we set them equal to each other. E to the x over 2 equals 1. So let's solve that. I'm going to square both sides to get rid of the fraction on the left. And e to the x equals 1, that's only going to happen if x equals 0. So x would have to equal 0. So they do intersect, and they intersect at 0. So that will be my starting limit. So I have a graph here that's starting at 0 and ending at 2. Now we want to figure out which one is on top and which one is on bottom. So we know that my integral is going to start at 0 and end at 2. It starts at 0 because that's where they intersect. It ends at 2 because that's the vertical line that they gave me to indicate where they stop. Now, how do I know which one's on top and bottom? Is it the e function or the y equals 1 function? Well, we're going to pick a number between 2 and 0. Obviously, a good choice would be 1. And we're going to plug it into each one of these functions. So if I plug it into the e function, I get e to the 1 over 2. And I can't plug 1 in here because it's just a number, so I'm going to put a 1 there. I keep putting an equal sign there, but we don't want an equal sign. The question is, are these things equal to each other? That they're not. Or are they greater than or less than? The one that's greater will be the one that's on top. The one that's less than is the one that's on bottom. So I want to know which one of these are greater. Well, that might not be obvious to you. But what we can do is we could square both of these to get rid of the fraction. And that would give me e and 1 instead. And if you remember that e is 2.71, you can see, oh, well, e must be the greater one. And so we know now that the e to the x over 2 is the top function, and the y equals 1 is the bottom function. And so I'm ready to set up my integral. We're going from 0 to 2, and we're going to do the top function minus the bottom function. And there's my integral. And I can stop there because they said write but do not evaluate. Okay, now you could even try to sketch the picture. You don't have to because we are done. We've accomplished our goal. But if you want to see what this picture would look like, we're only in the first quadrant, right? So I'm only going to draw the top right portion of a graph. Second of all, we're going up to x equals 2, so I'll draw a vertical line there as a boundary. My bottom function is y equals 1. These two functions cross at x equals 0, and I know that e is on top. So my graph would look something like this, and this would be the area that I'm finding here. Okay, so I have an integral that's going from 0 to 2 with the e on top of the 1. And the area between them would be that green shaded region. Okay, so there you have it. Here's one for you guys to do. Write but do not evaluate, so you don't need to actually solve it. Also, I don't want you guys to use a calculator. Try to do this without a calculator first. Okay? Pause the video here, and when you unpause it, I'll have everything all worked out for you. So here's the best answer, I'd say, is in the top right corner of our screen here. But let's talk about it a little bit. So I find where they intersect first by setting them equal. By adding the 2x squared over and subtracting the x over, I get 2x squared minus 6x. We could factor this by taking out a 2x, and then we set both of those things equal to 0 and solve. And these are my limits. So we're going from 0 to 3. Those are the limits of integration because that's the points where the graphs cross and stops the area. Next, we want to figure out which one top and bottom. So I pick a number between 0 and 3, and I plug it into each function. I chose to plug in 1, and I found out that the result is I get -1 for this function on the left and -5 for the function on the right. That means the function on the left is greater, so that means that this one is the top function. So we have that function minus a -5x. So now note, you might have missed the minus a negative here. That becomes a plus, and you can combine the 5x with the 6x with the regular x to get 6x. And so this is the best way to write your answer here. I even sketched a picture. I think this picture is a little bit more difficult to sketch, though, because it's not in the first quadrant. I do know that it starts at 0, and I know that it ends at 3. I also know this is a linear function, so it's negative, so it's going downwards, going through that 0 point. And this is a quadratic, which means it's a parabola, but it's a upside down parabola because it's a -x². That might be a little bit harder for you guys to sketch. You don't even really need to do it. I did that actually after I got this answer up here, but that's what the graph would look like if you wanted to take a shot at sketching it. All right, let's go ahead and move on to our last one here, which is an example of just how to use the calculator. So this one says, let R be the region bounded by this function and this function in the first and fourth quadrants. Okay. So the first thing I'm going to do is I'm going to graph this, and so I can have a picture of what I'm even trying to look at. All right, so we're going to go to our graphing calculator and graphs. So the first thing I do is I type these two functions in under y1 and y2 after pushing the y equals button, and then I push graph. And that's what they would look like. Now I only want to look at the first and the second quadrant. This is the first quadrant up here. I'm sorry, first and fourth quadrant. This is the first quadrant up here, and the fourth one is down here. So I only want to basically be looking at the right side of my graph. So I'm going to change my window here a little bit and zoom in the process. I don't need to see anything to the left of 0, so I'm going to have my x minimum be 0. And also when I look at the graph here, I really only want to find where they're intersecting, which is this little bubble here. So I'm only going to go up to like maybe x equals 2 here. Let's go up to x equals 2. And as for the y values, as you can see, I really only need to go up to y equals 2 and maybe y equals -2. So I'm going to go to my window here and adjust these. Is this necessary? No, but it sure makes a nicer picture if you do that. So I'm just going to change my x and y values here to 2s. And that way we have a cooler graph to look at. Okay, so there's that. So now I want to find out where they're intersecting. So how do you find out where they're intersecting? So you push second, calc, oops, wrong button, and get out of there. Second, calc, and you go down to intersect 5. And you're going to scroll over to where they're crossing. So I want to get the left-handed crossing point first. Right there. And just push enter 3 times. And it looks like we're intersecting at x equals 0. Okay. Let's go ahead and find the other intersection point. So second, calc 5. Let's scroll over to the other intersection point on the right side there. I'm going to push enter 3 times. And now I don't get such a nice number. So what I'm going to do is I'm going to write my integral out right now. We intersect at 0 and at 1.464. Now, even though the AP Calculus test only wants you to round up to the third number after the decimal, the thousands place, the problem is that this is not the answer. And if I use this calc in my calculation, I'm using a rounded number in my calculation, which will make my final answer off. So I want to store this value. How do we store again? You're going to push enter one more time, and then you're going to push store. Oh, I got to do it again. Just a second. I had to do that a few times for it to work out right, but after you get your answer, you just push enter, and then you push store, and it should take you back to the home screen where it says answer with an arrow. And I'm just going to store that as a letter. I'll call it A. So I'm going to push alpha, and then I'm going to click the A here, and then enter. So now A is 1.464. So my calculator stored the exact value. And that way, if I want to use this number, I can just type A in instead of my rounded number here, and it will give me an exact answer. All right. So back to our graph here. So I found where they cross, and I want to find this area between these two curves. Okay. So how do we do that? Well, we do the top function minus the bottom function. The top function is the blue line. Now, you might have forgotten which one that is. So if you don't remember which one that is, just push trace. And it says up here, as you scroll along, you can see that my cursor is tracing the blue line right now. And you can also see in the top corner here, it's telling you which function that is. So the one that's on top is the sine function. So I know it's going to be the sine of 2x is on top minus the x cubed minus 2x on the bottom. Okay, and there's my integral. That's what I'm going to type in. Now, on my calculator, though, sine of 2x is stored in as y1, and this one over here is stored as y2. And this thing up here is stored as a. So that's what I'm going to type in on my calculator. Now, if you're ever doing an FRQ problem, you're not going to put any of those in there. This is what you would want to write. But on your calculator, it's going to have those letters there instead. So let's go ahead and go back to our home screen. And we're going to type all that stuff in now. So we're going to do the integral. So math 9. We're going from 0 up to a. So you could put 1.464 here, but it will be slightly off, and that might cost you a point. So I'm going to do alpha a. That way it's got the exact intersection value there. And then we do the top function, which is y1. So I'm going to go to vars, scroll over to y vars 1, and put y1 minus y2. Put our dx in there and enter. And there's my final answer. That would be the area between the curves in those first two, in the first quadrant and the fourth quadrant. Okay. So let's review a couple of things here. So when you have a graphing calculator, first thing you do is you graph it, adjust the window if you want, find the intersection points. How do you do that? Second, Calc 5. And then once you find where they intersect, just push enter 3 times. Next, you want to store the value if it's a weird number, so you push enter and then store. And if you do that correctly, it'll take you back to the home screen. It'll say answer with an arrow. You just type alpha, B, A, or C, or whatever you want to type. Then you can use the trace button to see which function is on top. And by the way, if you ever want to have your cursor jump down to the other function, you just push down and it starts tracing the other one. It tells you what that one is. Okay. So that's how you can do it on a calculator, and we'll let you guys try one of these now. So go ahead and try this problem here. When you unpause the video, I will have the answer up for you. All right, so there's the graph. Here we're going from y equals 0. They intersect here. I adjusted my window to be at 0 for the x and 1.5 for the x, and the lowest y value is -1, the highest y value is 3. And the graph would look like that if you did that. This intersection point here is about 0.902. And since we're starting at the y-axis, that would be x equals 0. The top function is the the red line here, which is the cubic function of 2 minus x cubed. So it's 2 minus x cubed minus tangent x. Now, when you're being graded on an FRQ, we would look at this number. That would be worth a point. Also, having these things in the correct order would be a point. And then also getting the correct answer in the end would be a point. And then if you want to see how I got my answer, it's calculated here. I stored my intersection point of 0.902, and I typed it in like this. You'll also notice that I did y2 minus y1 instead of y1 minus y2. That's because this function on my calculator was stored under y2. If you got the same answer but it was negative, then you probably just typed these functions in backwards, like we said before. If you type them in backwards, you get the same answer, it's just negative. But anyway, On an FRQ, this would be like worth 3 points. You get 1 point for the intersection point, 1 point for the integrand being in the correct order, and 1 point for the final answer there. Okay? So there you guys have it. Hopefully it was helpful, and we'll practice this stuff in class. Till then, have a good one.